today we're going to be reviewing Riemann sums. In this case, we're going to be doing the area under the curve using rectangles. The question might look like, approximate the area between the graph y equals x squared plus 6 and the x-axis on the interval of -2 to 3 using n equals 5. Compute using left and right endpoints. So what this means is that we want to find the area between the x-axis and the little graph on the left that I've drawn. When they say n equals 5, that's referring to the number of rectangles. In the interval, -2 to 3 is going to be from what point on the x-axis are we going to and from. So when we're referring specifically to left endpoints, if you look at the graph that's drawn, we're going to take not an exact estimate using the rectangles because I want to meet the graph where it hits the axis on the left side. So, for example, in this case, I'm going to go up till I meet my graph and go across, and go up and go across, and the same thing moving forward. So, this is an approximation, not the exact area. And then if we were going to do the right endpoints, which I'm not going to draw, we would go up till it meets across and go down. And go up, across, and down. So that would create a different approximation. What we also need to know is the formula. The formula is the summation of the change in the width, which is delta x, which is equal to b minus a over n times the function plugged in for the various numbers on the interval. So since there are 6 numbers between -2 and 3, and we're only using 5 rectangles, we have to figure out what values for x we're going to use. In the case of left endpoints, we're going to use the 5 leftmost points. So in this case, we're going to use -2, -1, 0, 1, and 2 for our plugins for x. So what that would look like is if we do b minus a over n, -2 is equal to a, 3 is equal to b, and n is equal to 5. So, what that would look like is 3 minus -2 over 5, which becomes 3 plus 2, which would be 5 over 5, which is equal to 1. So what that tells us is that when we're setting up our area, the area is going to be equal to 1 times our plugged in values. So it's going to be 1 times f of -2 plus f of -1 plus f of 0 plus f of 1 plus f of 2. Now what that means is that I'm going to convert the f of the numbers into our y equals. So for example, area would be 1 times -2 squared plus 6, coming from our y equals x squared plus 6. In this case, x is going to be -2. Plus -1 squared plus 6 plus 0 squared plus 6 plus 1 squared plus 6 plus 2 squared plus 6. And that would conclude what our area is equal to. Then you would go ahead and compute that. So what that actually comes out to be is you would get 1 times 10 plus 7 plus 6 plus 7 plus 10, which would equal 40. So in this case, if we want to approximate the area using left endpoints, it would be area is equal to 40. Now what I want to do for the second part is use right endpoints. So let me go to another page. So once again, I want to create that little number line. So we have -2, -1, 0, 1, 2, and 3. So in this case, I want to use the rightmost points on this graph, which would be 3, 2, 1, 0, and -1. So we've actually computed the values for -1, 0, 1, and 2. So we can go back to the other page, and those were equal to 7, 6, 7, and 10. So we have area is equal to 1 times, no, not 10, hold on, 7, 6, 7, and 10 plus f of 3. So here we would have area is equal to 1 plus 7 plus 6 plus 7 plus 10 plus 3 squared plus 6, and that would be 15. So our area is equal to 1 times 7 plus 6 plus 7 plus 10 plus 15. So our area in this case would be equal to 45, which is a greater estimate than we found using the left endpoints. So if we graph that out, that would look something like this. So when we're using right endpoints, we're going to create our rectangles using the right side. So I'm going to go up to the right, go across. Go up to the right, go across. So here we have room for more overestimation than we did in the last case, which is why we have that greater number. So if we want to do right endpoints, our answer would be 45. So when we do left, it's 40, and when we do right, it's 45, which is why these are approximations. When you take the actual integral, you'll get the actual area under the curve.